In this video, we introduce our work, Pose. Our goal is to recover human body meshes and 3D joint rotations from sensor data, like a single image. Existing works include direct methods that regress rotation directly, and indirect methods that predict intermediate proxies and then obtain joint rotation. However, high precision and robustness cannot be achieved simultaneously. To address it, probabilistic models consider rotation uncertainty. Prevalent ways include Gaussian distributions and implicit manners. However, they are not constrained to SO3. A recent work learns the distribution on SO3 directly, but the performance is limited. Therefore, we need a model that is probabilistic, on SO3 and easy to learn. We derive the posterior probability of joint rotations and prove its effectiveness in human mesh recovery and multi-sensor fusion. Let's dive into the algorithm. We pay attention to two cases of orientations, one is rotational, and the other is directional. First, we introduce the rotation distribution. For rotation matrix R in SON, the matrix Fisher distribution has been proposed to characterize its probabilistic properties. F is the distribution parameter and has the same dimension as R. And Cf is a normalizing constant. Tr is the matrix trace. The parameter F can be decomposed into a concentration term K and a mean rotation term M with SVD decomposition. Delta is to ensure the determinant of M is 1. Given an F, the mean term M can be regarded as a rotation estimation. Next, we introduce the direction distribution. The probability density function for a unit vector d on n-1 sphere has a similar formulation. It corresponds to the classical von Mises-Fisher distribution. Kappa and M are concentration term and mean direction term. And they have the same role as those in matrix Fisher distribution. Here are some intuitions. Theoretically, if kappa is 0, it is equivalent to the uniform distribution on the sphere, while if kappa is large, it is close to the wrapped normal distribution that adds up the densities of vectors representing the same direction on the sphere due to the periodicity. Thus, kappa can be viewed as the inverse of the variance and denotes the concentration of the distributions. With the above preliminaries, we can derive the posterior probability in a Bayes manner based on these facts. First, joint rotations follow the matrix Fisher distribution on SO3. Second, bone directions follow the von Mises-Fisher distribution on S2. Third, bone direction can be viewed as the observation of joint rotation, that is the latent variable. Given prior and likelihood, the posterior probability can thus be calculated. Here are the details of the derivation. In the formulation of likelihood, L is the unit direction of the bone in the reference pose, for example, T-pose. And R, rotate L, to the current direction D. It can be concluded that the posterior probability of joint rotations conditioned on bone directions is controlled by a new parameters F', consisting of prior parameter F, current bone direction D and its confidence kappa, and canonical bone direction L. Furthermore, a property can be derived. Posterior parameter F' can be reformulated as the multiplication of the same mean term M and a new concentration term K'. Two components of K' are both real symmetric. And the rank of the right term is 1. According to interlacing theorem, it can be proved that the eigenvalues of K' are larger than the eigenvalues of K. As the eigenvalues of concentration term reflect the confidence of the distribution, we can conclude that the posterior estimation is more concentrated than the prior estimation. For other sensors, like directional sensor accelerometers and rotational sensor gyroscopes, they can also be incorporated to improve the accuracy. The analytical posterior probability can be derived similarly. This schematic diagram can help recognize the proposed scheme intuitively. For a method without probabilistic modeling, its underlying model is a single direction, thus it may be erroneous when the estimated bone direction deviates from the ground truth. In contrast, the posterior model can be fused with various models, and for noisy key points, it has the potential to recover the exact rotations. Based on the derivation, we propose our framework. Given an input image, the multi-branch network predicts the prior matrix Fisher parameters f, the 3D key points j, and the SMPL shape parameters beta, respectively. The bone direction d calculated from j serves as the likelihood conditioned on 3D rotation. The posterior probability can be obtained based on Bayesian rules, which still follows the matrix Fisher distribution, but with different parameters and larger confidences. Observations from additional sensors can also be fused into the posterior probability in the same manner. The corresponding human mesh can then be recovered using the estimated rotation and shape. Our objective functions include joint loss, shape loss, pose loss, and sampling loss. The sampling loss is used to supervise the distribution through rejection sampling. We perform experiments on 3DPW, human 3.6M and Agora datasets and outperform previous methods. On Agora, 2 concurrent works are shown in gray for completeness. The ablation study reveals the importance of each branch. If keypoint branch or the prior branch is discarded, the performance will degrade apparently. Besides, if we deactivate the learned prior parameters only in testing as C shows, its performance will be better than B, indicating the prior F has guided the keypoint's learning to some extent. The right figure shows the performance of different sensors and baseline methods. We evaluate the robustness of our framework when suffering from noise. Both the simulation and practice show the error increases more slowly than IK-based methods. Now we show some qualitative results. Thanks for watching.